Hello, in this lecture we will find the area of a circle. In the drawing we have a circle and inside the circle we have a shape ADCB is a shape. Actually, angle ADC is a right angle and it equals to 90 degrees, and also angle BCD is a right angle and it equals to 90 degrees. And side BC of this shape equals to 8 units, side DC equals to 6 units, and side AD of this shape equals to 4 units. And we want to find out the area of this circle. First of all, I will explain you the theorem one-sided angle. If we have two lines, line A and line B, this is line A, and this is line B, and we have a third line, line C, that intersects those two lines at points M and N. The point of intersection between line C and line A is M, and the point of intersection between line B and line C is N. Then we have two angles, angle alpha and angle beta. Actually, angles alpha and beta are defined as one-sided angles because of the fact that both of them located in the left side of angles alpha and beta. Okay, both angle alpha and beta located in the left side of line C. For that reason, angles alpha and beta are defined as one-sided angles. Actually, these angles alpha and beta are defined as internal angles. So I will write it down. Angles alpha and beta are internal angles, one-sided angles. Again, angles alpha and beta are defined as interior one-sided angles. Why they are one-sided? Because they both located in the left side of line C. For that reason, they are called one-sided. And they are inside actually inside B and A, so they are defined as one-sided interior angles. While if you have two lines A and B, this is line A, and this is line B, and you have line C that intersects lines A and B in points M and N. Okay, so actually here angles alpha and beta are defined as exterior one-sided angles. Okay, so I write it down. Okay, first of all, both angles alpha and beta located in the left side of line C. For that reason, they are one-sided angles, and they are actually outside line B and line A. For that reason, they are defined as exterior one-sided angles. Okay, so again, those two angles, alpha and beta, are defined as interior one-sided angles, while those two angles are defined as exterior one-sided angles, and those two angles are defined as interior one-sided angles. Okay, so that is the definition of one-sided angles. They are one-sided because they called one-sided because they are located in one side, in the same side of line C. They are both in the left side. So if they were both in the right side, they are also defined as one-sided, because of the fact that those two angles in the same side of line C, they are defined as one-sided angles, and those angles are exterior because they are outside the lines A and B, while those angles alpha and beta are interior one-sided angles because they are inside the lines A and B. Okay, so that is the definition of one-sided angles. And actually we have a rule, I will call it rule number 1. And rule number 1 states that if the sum of the one-sided angles equals to 180 degrees, then line A is parallel to line B. So I write it down. If the sum of two one-sided, they could be interior or exterior. It doesn't matter whether they are interior or exterior. So I write it down. They can be interior or exterior angles. So if the sum of two one-sided, they can be interior or exterior angles, equal to 180 degrees, then line A is parallel to line B. Okay, so I will read again rule number one. Rule number one states that if the sum of two one-sided, they can be interior or exterior, if the sum of one-sided angles equal to 180 degrees, then A is parallel to B. If the sum of one-sided angles equals if the sum of two one-sided angles equals to 180 degrees, then line A is parallel to line B. So actually, we can see in the drawing two exterior angles, one-sided angles. So if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay, so according to rule number one, if the sum of angles alpha and beta, that is to say alpha plus beta, equals to 180 degrees, then line A is parallel to line B. Okay, and the same rule applies to the interior one-sided angles. It is the same rule. So if alpha plus beta equals to 180 degrees, so if the sum of the one-sided interior angles equals to 180 degrees, then line A is parallel to line B. According to rule number one. Okay, the same rule applies to interior one-sided angles. Those two interior one-sided angles, if the sum of those two interior one-sided angles equals to 180 degrees, then line A is parallel to line B. Okay, so actually we can implement rule number 1 in our circle, because we have angle ADC is a right angle. This is a right angle. That is to say, it equals to 90 degrees. And angle BCD is also a right angle, so it equals to 90 degrees. So actually the sum, they are both one-sided internal angles. Actually you can see line segment DC as line C. Okay, line segment DC can be viewed as line C, and while AD can be viewed as line A, and BC can be viewed as line B, and line segment DC can be viewed as line C. So actually those two angles are one-sided internal angles, because they are from the left side of line segment DC that is considered as line C. They are from one side, for the left side of line segment DC. For that reason, those two angles are one-sided internal angles. Okay, so actually angle ADC equals to 90 degrees plus angle BCD also equals to 90 degrees, and they are one-sided internal angles. They are from the left side of line segment DC that can be viewed as line C. This is line C, and these two angles are one-sided angles because they are from the left side of line C, and those two angles both are from the left side of line segment DC. For that reason, they are one-sided internal angles, and the sum of those two angles equals to 180 degrees. For that reason, according to rule number 1, AD is parallel to BC. Okay, AD is parallel to BC according to rule number 1. So we can write here that according to rule number 1, rule number 1 that states that if the sum of one-sided angles equals to 180 degrees, then A is parallel to B. So according to rule number 1, AD is parallel to BC. line segment AD is parallel to line segment BC. Okay? So we know that AD is parallel to BC. In the next step, we will connect together. In the next step, we will connect together points A and C by a straight line. And we will also connect together points B and D by a straight line. Okay, so we connected together points A and C by a straight line. We created line segment AC, and we connected together points D and B by a straight line, and we created line segment DB. In the next step, we will focus on triangle B. First of all, we will define the intersection between line segment DB and line segment AC as point O. Again, we defined the intersection between line segment AC and DB as point O. This point is defined as point O. And in the next step, we will focus on two triangles, triangle BOC and triangle AOD. I will paint them in the green light, green color. So we will focus on the green triangle BOC, the big green triangle BOC, and the small green triangle AOD. Okay, so we will focus on those two triangles, green triangles, the big triangle BOC and the small triangle AOD. Actually, we will prove that those two green triangles are similar to each other, and therefore they have a special relationship between their sides. In order to prove that those two green triangles are similar to each other, we have to prove that three angles of the big triangle equal to three angles of the small green triangle. Okay, so we'll do it now. Actually, angle AOD, this angle, equals to angle BOC. I will write it down. This angle equals to this angle. I will write it down. Angle AOD equals to angle BOC. This angle equals to this angle again. Angle AOD equals to angle BOC. Because of the fact that those two angles are vertex angles, we have rule number 2 that states that vertex angles are equal to each other. So according to rule number 2, angle AOC equals to angle BOC. This angle equals to this angle. So I'll write here, the reason that those two angles are equal to each other is according to rule number 2 that states that vertex angles are equal to each other. They are vertex angles and vertex angles are equal to each other. Okay, now I will explain you what is a vertex angle. Actually, when two lines when two lines are intersecting with each other, for example, line A intersects with line B, the point of intersection is this point. So at the point of intersection, at this point, they create four angles. I will call this angle angle 1. This angle will be called angle 2. This angle will be defined as angle 3, and this angle will be defined as angle 4. Okay, actually angles 1 and 3 are vertex angles and they are equal to each other according to rule number 2. So I write it down. Angles 1 and 3, those two angles are defined as vertex angles, and according to rule number 2, vertex angles are equal to each other. Angle 1 equals to angle 3 according to rule number 2. Okay, so angle 1 and angle 3 are vertex angles, and according to rule number 2 they are equal to each other. Angle 1 equals to angle 3 according to rule number 2. And also angle 2 and angle 4 are defined as vertex angles and they are also equal to each other. angle 2 and angle 4 are vertex angles, and they are equal to each other according to rule number 2. Okay, angle 2 and angle 4 are vertex angles, and they are equal to each other according to rule number 2. The angle 2 and 4 in the red color are vertex angles, and they are equal to each other according to rule number 2. So I will write rule number 2. I write it down. Rule number 2 states that vertex angles are equal to each other. Very simple. I will read rule number 2 again. According to rule number 2, vertex angles are equal to each other. So if we have two lines that are intersecting with each other, they create two pairs of vertex angles, and those two pairs are equal to each other. Angle 1 equals to angle 3, and angle 2 equals to angle 4. So for example, we have those two lines that intersect with each other at this point and create two pairs of vertex angles. So the first pair of vertex angles are those angles alpha and beta. Alpha and beta are vertex angles, and therefore they are equal to each other. Alpha equals to beta according to rule number 2. Okay, so angles, this is the first pair, and then in the next step I will show you the second pair of angles pairs that are equal to each other. So this is the first pairs of angles, of vertex angles. Angles alpha and beta are vertex angles, and therefore according to rule number 2 they are equal to each other. So angle alpha equals to angle beta. And the second pair of vertex angles again, vertex angles created when two lines intersect with each other. They create two pairs of vertex angles. So this will be the second pair of vertex angles. So this was the first pair, and this is the second pair of vertex angles. Again, alpha and beta are vertex angles. And alpha equals to beta according to rule number 2. Okay, this is the second pair of angles, alpha and beta, that are equal to each other according to rule number 2. This is the first pair of angles alpha and beta that are equal to each other, and this is the second pair of angles alpha and beta that are equal to each other because of the fact that vertex angles are equal to each other according to rule number 2. Okay, so we actually implemented rule number 2 in our circle, because as you can see from the drawing, angle AOD and angle BOC are vertex angles, and therefore they are equal to each other. Okay, so I'll write it again. First of all, we are focusing on those two green triangles. Triangle BOC and triangle AOD. Okay, so we have in those two triangles angle AOD, this angle AOD equals to angle BOC, because those angles are vertex angles, and vertex angles are equal to each other according to rule number 2. Okay, so we have the first equality. It states that angle AOD equals to angle BOC because of the fact that vertex angles are equal to each other. I will add here that it is true according to rule number 2. Okay, according to rule number 2, this angle equals to this angle because of the fact that vertex angles are equal to each other. In the next step, I will explain the theorem alternating angles. Actually, if we have two lines, line A and line B, this is line A and this is line B, and we have a third line, line C, that intersects with those two lines. Line C intersects with lines A and B. in these 2 points. Those are the intersection points, this point and this point. Actually, here we have angle alpha and angle beta. We actually know that line A is parallel to line B, and only then alpha and beta will be defined as alternating internal angles. Okay, so alpha and beta, if A is parallel to B, line A is parallel to line B, then angles alpha and beta are defined as alternating interior angles. Again, if line A is parallel to line B, then angles alpha and beta are defined as alternating interior angles. So when we talk about alternating angles, they must be, first of all, line A must be parallel to line B, and then angle alpha will be in the opposite direction of angle beta in relation to line C. As you can see here, angle alpha and angle beta are in different positions in relation to line C. So if we say that angle alpha is in the right side of line C, then angle beta is in the left side of line C. So in relation to line C, angles alpha and beta are in opposite locations. If this angle is in the right side, this angle in relation to line C, this angle is located in the left side of line C. Okay, they are in opposite directions in relation. They are located in opposite locations in relation to line C. Okay, for that reason they are called alternating angles, and those two angles alpha and beta are interior alternating angles. So actually, in order that angles alpha and beta will be defined as alternating angles. Line A must be parallel to line B. Only then angles alpha and angle beta will be defined as alternating interior angles. And according to rule number 3, alternating interior angles between parallel lines, line A is parallel to line B, alternating interior angles between parallel lines are equal to each other. So we know that line A is parallel to line B, and therefore, according to rule number 3, angle alpha equals to angle beta. Okay, so I will write it down. So only if line A is parallel to line B, angles alpha and angles beta are defined as alternating angles, and alternating angles are equal to each other, according to rule number 3. Okay, so line A must be parallel to line B, and only then angle alpha equals to angle alpha and beta, angles alpha and beta are defined as alternating angles, and actually according to rule number 3, alternating angles between parallel lines are equal to each other. Okay, and alpha equals to beta according to rule number 3. Okay, this the other possibility is that we have exterior alternating angles and actually exterior alternating angles are equal also to each other. Okay, so we can write down that if we have two angles, if we have two lines, line A and line B, this is line A, and this is line B, and we have third line, line C, that intersects line A and B. We have line C that intersects lines A and B at these 2 points. We actually know that line A is parallel to line B. Okay, line A is parallel to line B, and therefore angle alpha and beta are defined as exterior alternating angles. I write it here. Alpha and beta are exterior alternating angles. We'll emphasize this point that line A must be parallel to line B. Otherwise, angles alpha and beta will not be defined as alternating angles. Angles alpha and beta will be defined as alternating exterior alternating angles only if A is parallel to B. Only if line A is parallel to line B, then angles alpha and beta will be defined as exterior alternating angles. And actually, according to rule number 3, alternating exterior angles between parallel lines, that is to say line A is parallel to line B, are equal to each other. Okay, according to rule number 3. So I will write down rule number 3. So rule number 3 states that alternating angles between parallel lines are equal to each other. I have already showed you the examples. So I will read rule number 3 again. Rule number 3 states that alternating angles between parallel lines are equal to each other. So actually, as I've already told you, first of all, line A must be parallel to line B, and only then when line C intersects those two parallel lines, then angles alpha and beta will be defined as alternating angles, and according to rule number 3, alternating angles between parallel lines are equal to each other. We know that line A is parallel to line B. Only then alpha and beta will be defined as alternating angles, and according to rule number 3, alternating angles between parallel lines are equal to each other. For that reason, angle alpha equals to angle beta. Those two angles are interior alternating angles between lines A and B that are parallel to each other, and therefore they are equal to each other. They are equal to each other according to rule number 3. And also we have exterior alternating angles. We know that line A is parallel to line B, and those two angles, only then those two angles will be defined as exterior alternating angles. And according to rule number 3, exterior alternating angles between parallel lines, line A is parallel to line B, are equal to each other. Okay, so we actually can implement rule number 3 in our circle, because we know that line segment AD is parallel to line segment BC. This line segment is parallel to this line segment. So, according to rule number 3, actually, according to our definition, this angle OAD, and angle BOC, those two angles are alternating angles between parallel lines. We know that AD is parallel to BC, so those two angles are located in the opposite sides in relation to AC. They are in opposite sides in relation to line AC. So for that reason they are defined as alternating angles, and according to rule number 3, alternating angles between parallel lines are equal to each other. AD is parallel to BC, and those two alternating angles are equal to each other according to rule number 3. So we can write down that angle DAO equals to angle BCO according to the rule number 3 that states that alternating angles between parallel lines are equal to each other. So I write here that alternating angles okay, again, angle DAO equals to angle BCO because of the fact that those two angles are alternating angles between parallel lines, and they are equal to each other according to rule number 3, because according to rule number 3, alternating angles between parallel lines are equal to each other. Okay, and the third angle, angle CBO and angle ADO, those two angles in the red color are alternating angles. Okay, actually they are located in opposite sides to line segment DB. Actually, line segment DB is like the line C that intersects with lines A and B. So here DB intersects with the two parallel line segments AD and BC. AD is parallel with line segment BC, and line segment DB intersects those two line segments that are parallel to each other. The points of intersection is point D and point B, so for that reason those two angles are alternating angles, and according to rule number 3, alternating angles between parallel lines are equal to each other. So we can write down that angle CBO also equals to angle ADO according to rule number 3. Angle CBO equals to angle ADO, those two red angles, angle ADO. For the same reason, those two angles are alternating angles between parallel lines and they are equal to each other according to rule number 3. Okay, right here. Okay, so we proved that angle CBO equals to angle ADO because of the fact that those two angles are alternating angles between parallel lines. AD is parallel to BC, and therefore according to rule number 3 they are equal to each other. Okay, so actually we proved that 3 angles of the green triangle are equal to 3 angles in the small to 3 angles of the small triangle, small green triangle. This angle equals to this angle equals to this angle, and this angle equals to this angles. So 3 angles of this green triangle are equal to 3 angles of this small green triangle, and therefore those two green triangles are similar triangles. So we can write down that according to AAA, that is to say A is abbreviation for angle, three angles of this triangle are equal to 3 angles of this triangle. So according to AAA, the big green triangle COB is similar to the small green triangle AOD. Okay, so according to AAA, triangle COB, the big green triangle, is similar to triangle AOD, the small green triangle, because 3 angles of the green big triangle are equal to 3 angles of this small green triangle. So actually, if we have two triangles that are similar to each other, then we have special relationship between their sides. Okay, so I'll show you the relationship between the sides of two triangles that are similar to each other. So actually, if we have two triangles, the big triangle ABC is similar to the small triangle DEF, we have the following relationship between the sides of those two triangles, those two similar triangles. AB over DE equals to BC over EF equals to AC over DF. Okay, so if we have two triangles that are similar to each other, we have this relationship between their sides. AB over DE equals to BC over EF, and it equals to AC over DF. Okay? This is the relationship that is true whenever you have two triangles that are similar to each other. Okay? So we actually can implement the rule in the rule of similar triangles in our circle, because we have two green triangles that are similar. We have already proved that those two green triangles are similar to each other. Therefore, we can use the spatial relationship between the sides of those two green triangles, and we can write down that OB over OD equals to OC over OA, and it also equals to BC over AD. Okay, this is the relationship between of the sides of these two green similar triangles. OB over OD equals to OC over AO, that equals to BC over AD. Okay? Okay, that is the relationship between those two similar green triangles. And but we know that BC equals to 8 units and AD equals to 4 units. So we can write here that BC equals to 8 units while AD equals to 4 units. 8 over 4 is 2. Okay, so we have this relationship in those two similar triangles. So we can write here that OB over OD equals to 2. OB over OD equals to 2. That is to say, if we multiply this equality by OD, OB equals 2 times OD. OB equals 2 times OD. So if OD equals to A, then OB equals 2 times OD. So OB will be equal 2 times A. Okay? OB equals 2 times OD. So if OB equals to A, then OB equals 2 times A. Okay, and also we have the second equality that states that OC over OA equals to 2. Here we can multiply this equality by OA. We'll get that OC equals 2 times OA. OC equals 2 times OA. So if, for example, OA equals to B, then OC equals 2 times OA. So OC equals 2 times B. Okay, if OA equals to B, then OC equals 2 times OA. That is to say, OC equals 2 times B. Okay. So, in the next step, we know that angle ADC, this angle, equals to 90 degrees. So, because of the fact that angle ADC equals to 90 degrees, then triangle ADC is a right triangle. Okay, triangle ADC is a right triangle. So we can implement the Pythagorean theorem in the right triangle ADC. Okay. Okay, we know that angle ADC equals to 90 degrees, therefore triangle ADC is a right triangle. Therefore we can implement the Pythagorean theorem on the right triangle ADC. Okay, according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square, that is the hypotenuse, that is the square of the hypotenuse, AC square. The hypotenuse is AC, so the square of the hypotenuse is AC square, equals to the sum of the squares of the perpendiculars, equals to AD square plus DC square. Okay, again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is to say, AC square equals to AD square plus DC square. Okay, that is according to the Pythagorean theorem in the right triangle. We implemented the Pythagorean theorem in the right triangle ADC. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay. AC equals to B plus 2B is 3B. So AC square is 3B square equals to AD square. AD is 4, so AD square is 16 plus DC square. DC equals to 6, so DC square is 36. So in total we got that 3B square equals to 16 plus 36. 16 plus 36 is 52, so I write it down. Okay, we got that 3B square equals to 52. Now I will take a root out of this equality. We'll get that 3B equals to the root of 52. So we got that 3b equals to the root of 52. Now 52 is 13 times 4, so I write it down and I will split the root to two roots. So, as I already said, 52 equals to 4 times 13. The root of 4 is 2, so I write it down. So we got that 3b equals to root of 4 is 2, 2 times root 13. We will divide this equality by 3 and we will get the value of b. So we divided this equality by 3, we got that b equals to 2 over 3 times root 13. If b equals to 2 over 3 times root 13, the 2 times b equals to 4 over 3 times root 13. So we actually can write here that b equals to 2 over 3 root 13, while 2 times b equals to 4 over 3 root 13. Okay, so we found out the value of b, or also the value of line segment AO and OC, and we know the value of line segment AC. So in the next step we will implement the Pythagorean theorem on this right triangle. Actually, angle BCD is a right angle. It equals to 90 degrees. Angle BCD equals to 90 degrees. Therefore, triangle BCD is a right triangle. So we can implement the Pythagorean theorem in the right triangle BCD in the same way like we did before. The square of the according to the Pythagorean theorem, the square of the hypotenuse, that is to say dB square or BD square, equals to the sum of the squares of the perpendiculars, equals to DC square plus BC square. Okay, so we have the square of the hypotenuse is dB, so the square of the hypotenuse is dB square, equals to the sum of the squares of the perpendiculars, equals to DC square plus BC square. Again, according to the Pythagorean theorem, in the right triangle BCD, the square of the hypotenuse is dB square. That is dB square. That is the hypotenuse is dB, so dB, the square of the hypotenuse is dB square, equals to the sum of the squares of the perpendiculars, equals to this square plus BC square. Okay, dB square equals to DC square plus BC square. But dB equals to A plus 2A is 3A, so dB square is 3A square equals to DC, DC equals to 6, DC square is 36, plus BC square. BC equals to 8 units, so BC square is 64. In total we got that 3A square equals to 36 plus 64. 36 plus 64 is 100, so I will write it down. So we got that 3A square equals to 100. We'll take a root out of this equality. The root of 100 is 10. We got that 3A equals to 10. 3A equals to 10. We will divide this equality by 3 and we will get the value of A. So we divided this equality by 3, so A equals to 10 over 3. If A equals to 10 over 3, then 2 times, made a mistake, then 2 times A equals to 20 over 3 units. Okay, so we can write here that A equals to 10 over 3, while 2 times A equals to 20 over 3 units. Okay, so we actually found out the values of all the line segments in this circle. Okay, so in the next step I will copy this drawing in this page because we don't have enough space for all the numbers here. We have already found the values of A and B, so A and B are not needed. Anymore. Okay, so I copied this drawing to this page. It is exactly the same except of the color. Okay, so we know all the sizes of all the line segments in this inside this circle. In the next step, we will extend line segment AC until it touches the circle at point, let's say point P. Again, we will extend line segment AC until it touches the circle at point P. Okay, we extended line segment AC until it touches the circle at point P, and in the next step we will calculate the value of the new line segment that we created. That is to say, we will calculate the value of line segment CP. In order to calculate the value of line segment CP, we need to use a new rule. I will call it rule number 4. Okay. So, according to rule number 4, if two chords are intersecting each other, let's say chord AB intersects with chord CD, and the point of intersection is point O. Again, chords AB and CD are intersecting, and the point of intersection is at point O. Then the following equality is true according to rule number 4. Actually, in the intersection point, the following equality is created. AO times OB AO times OB equals to CO times OD. So again, if we have inside the circle two chords that are intersecting each other at point O, point O is the point of intersection, then the following equality is true, that AO times OB equals to CO times OD. That is rule number 4. So I write down rule number 4. According to rule number 4, if two chords are intersecting each other, at point O is the point of intersection. So actually, if two chords AO and OB okay, if two chords, that is to say chord chord AB and chord CD, okay, if two chords, that is to say chord AB and chord CD, okay, so if two chords, chord AB and chord CD, are intersecting each other at point O is the point of intersection, then the following equality is true. AO times OB equals to CO times OD. AO times OB equals to CO times OD. Okay, AO times OB equals to CO times OD. Okay, this is the equality that is true if two chords are intersecting each other at point O. If two chords, chord AB intersects with chord CD at point O, then the following equality is true. That is to say AO times OB equals to CO times OD. That is rule number 4 that we can implement in our circle. Here in our circle we have chord AP that intersects with chord DB at point O. So according to rule number 4, because we have two chords that are intersecting each other at point O, then AO times OP equals to DO times OB. Okay, so I write it down. Chord AP intersects with chord DB at point O. Point O is the point of intersection between those two chords. Therefore, according to rule number 4, AO times OP equals to DO times OB. So I'll read again the things that I wrote. Chord AP intersects with chord DB at point O. Therefore, according to rule number 4, AO times OP equals to DO times OB. Again, chord AP intersects with chord DB. Chord AP intersects with chord DB at point O. Point O is the point of intersection. Therefore, according to rule number 4AO times OP equals to DO times OB. Okay, so we know that AO equals to 2 over 3 times root 13. OP equals to OC plus CP. OP equals to OC plus CP. DO equals to 10 over 3. While OB equals to 20 over 3. So in total we got that 2 over 3 times root 13 times OC plus CP, that is actually OP equals to OC plus CP equals to DO is 10 over 3 while OB is 20 over 3. Actually we have in the denominator 3 in this side of the equation, in the other side of the equation we have also 3, so we can cancel 3 in the denominator. So what is left is, here we have 2 times, first of all I will write down the value of OC. OC actually equals to 4 over 3 times root 13, so I write it down. OC equals to 4 over 3 times root 13. Okay, so I write it down. So here I substituted OC by 4 over 3 times root 13, and 3 is cancelled, so in total we got 2 times root 13 times CO. 2 times root 13 times CO is 4 over 3 times root 13, plus CP is the only line segment that we don't know, and we will find by solving this equation. While 2 times 10 is 200, so in total we have here 200 over 3, okay? And now we'll open the brackets here. Root 13 times root 13 is 13, and 2 times 4 is 8. So I write it down. So we open the brackets again. Root 13 times root 13 is 13, and 2 times 4 is 8. So in total we got that 8 times 13 over 3 equals to 200 over 3. 8 times 13 is 104, so I will write it down. Again, 2 times 13 is 104. In total we have here 104 over 3 plus 2 times 13 equals to 200 over 3. So here I will subtract 104 over 3 from this equality. Here I forgot the CP. Two times root 13 times CP, okay? CP, here we have CP and CP. Okay, so we got that 2 times root 13 times CP equals to 200 minus 104 is 96. In total we have here 96 over 3. And 96 over 3 is 32, so I write it down. Okay, we have here 2 over 13 times CP equals to 32. We divide this equality by 2. So we got that root 13 times CP equals to 16. Now we will divide this equality by root 13 and we will get the value of CP. Okay. So we divided this equality by root 13 and we got that CP equals to 16 over root 13 units. So we can write here that CP equals to 16 over root 13 units. Okay, so we found out the value of CP. In the next step, we will extend line segment DC until it touches the circle at point Q. Okay, here we extended line segment DC until it touches the circle at point Q. So we created new line segment CQ, and we again in the same way we will calculate the value of line segment CP, the size of CP, according to our fourth rule that states that if two chords are intersecting each other at point O, then we have a special relationship between at the point of intersection, AO times OB equals to CO times OD. Okay, so we actually have line segment DQ intersects with line segment AP, and the point of intersection between those line segment AP intersects with line segment DB at point O. Okay, line segment DQ intersects with line segment AP, and the point of intersection is at point C. Okay, the point of intersection is at point C. So according to rule number 4, we can say that DC times CQ equals to AC times CP. Okay, according to rule number 4, DC times CQ equals to AC times CP. Okay, DC equals to 6 units. CQ is the segment line that we want to find out, so I will leave it as it is. Equals to AC equals to 2 over 3 times root 13 plus 4 over 3 times root 13. And CP, we have already found out the value of CP. CP equals to 16 over 13 units. Okay, so in total we got that 6 times CQ equals to 2 over 3 times root 13 plus 4 over 3 times root 13 times 16 over root 13. Okay. Actually, we have, first of all, 2 over 3 times root 13 plus 4 over 3 times root 13 equals to 6 over 3 times root 13, so I write it down. So, as I've already told you, 2 over 3 times root 13 plus 4 over 3 times root 13 equals to 6 over 3 times root 13. And here we have root 13 in the numerator, and we have also root 13 in the denominator, so we can cancel root 13. So we cancelled root 13. Here we left with 6 over 3 times 16. 6 over 3 is 2, so I write it down. So 6 over 3 is 2, and 2 times 16 is 32, so I write it down. we got that 6CQ equals to 32. I will divide this equality by 6. So we divided this equality by 6. We got that CQ equals to 32 over 6. We can divide the numerator and the denominator by 2. We will get that CQ equals to 16 over 3 units. Okay, so we can write here that CQ actually 16 over 3 is 5 and third. So instead of 16 over 3 we can write here that 5 third units. And in the next step we will extend line segment BC until it touches the circle at point R. Okay, we extended line segment BC until it touches the circle at point R, and we created new line segment RC. And in the next step, like we did before, we will calculate the value of the new line segment RC according to the fourth rule. Actually, chord DQ intersects with chord RB or BR at point C. Point C is the point of intersection between those two chords. Therefore, according to rule number 4, DC times CQ equals to RC times BC, or BC times RC. I'll read again what I wrote. Chord DQ intersects with chord RB at point C. Chord DQ intersects with chord RB at point C. Therefore, according to rule number 4, DC times CQ equals to BC times RC. Okay, DC times CQ equals to BC times RC. DC equals to 6 units, CQ equals to 5 thirds, BC equals to 8 units, RC is the only line segment that we want to find out. We don't know its value, so we will find out the value of RC by solving the equality. Okay, so in total we got that 6 times 5 thirds equals to 8 times RC. Or it is better to write it 16 over 3 equals to 8 RC. Okay, instead of 5 thirds, I wrote 6 times 16 over 3 equals to 8 RC. Here 6 over 3 is 2, so I write it down. So 6 over 3 is 2. In total we got here in the side of the equation 2 times 16 equals to 8 times RC. 2 times 16 is 32, so I write it down. So 16 times 2 is 32. In total we got that 32 equals to 8 times RC. Now we will divide this equality by 8 and we'll get the value of RC. (32 over 8 equals to 4), so the value of RC is 4 units. So we can write here that the value of RC is 4 units. Okay, so we actually found out the values of all the line segments in this circle. And the only thing that is missing is the radius of this circle. After we will find the value of the radius of this circle, we will easily find out the area of this circle, because the radius of any circle equals to pi times r square. Okay, so in order to find out the value of the circle, we will implement rule number 5 in this circle. According to rule number 5, if two chords are intersecting at 90 degrees, we have, for example, chord AB that intersects with chord CD at point O at 90 degrees. Okay, chord AB intersects with chord CD at point O at 90 degrees. So according to rule number 5, the following equality is true in this situation. 4 times R squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay, so if whenever we have in a circle two chords that are intersecting with each other at 90 degrees, then at the point of intersection we have the following relationship between the line segments. 4 times the radius of the circle squared equals to AO squared times BO squared times CO squared times DO squared. Okay, so I will write down rule number 5. According to rule number 5, if two chords in the brackets I will write AB, chord AB and chord CD, are intersecting at 90 degrees, at point O, then the following equality is true. Four R squared equals to AO squared plus BO squared plus CO squared plus DO squared. So I will read again rule number 5. Rule number 5 states that if two chords, in our specific case is AB and CD, are intersecting at 90 degrees, those two chords AB and CD are intersecting at 90 degrees, that is to say the angle between them equals to 90 degrees. Actually all the four angles are here is 90 degrees, so they create between in the point of intersection 90 degrees. Then the following equality is true. 4r squared equals to a o squared plus b o squared plus c o squared plus d o squared. 4r squared, that is to say 4 times the radius of the circle squared, equals to a o squared plus ob squared plus co squared plus do squared. Okay, so we can implement this rule number 5 in our circle, because in our circle angle BCD equals to 90 degrees. Therefore, chord RB intersects with chord DQ at 90 degrees. Chord RB intersects with chord DQ at 90 degrees. And the point of intersection is at point O. Therefore, according to rule number 5, four r squared equals to dc squared plus cq squared plus dc squared plus rc squared. I will read again the things that I wrote. Chord RB intersects with chord DQ at 90 degrees. Chord RB intersects with chord DQ at 90 degrees. This angle is 90 degrees. All the angles here are 90 degrees, and the intersection point is at point C. Okay, point C. Therefore, according to rule number 5, dc squared plus cq squared plus bc squared plus rc squared equals to 4 times r squared, when r is the radius of this circle. Okay, so the only missing variable here is r in this equation. So we can write down that 4 times r squared equals to dc square. Dc equals to 6 units, so dc square is 36 plus cq. cq is 5/3, so cq square is actually 28.44 plus dc square plus bc square bc equals to 8, so 8 square is 64 plus rc square. R equals to 4, so r square is 4 square is 16. So in total we got that 4r square equals to 36 plus 28.444 plus 64 plus 16. 36 plus 64 is 100. And 116 is 116, and 116 plus 28.444 equals to 144.444. So in total we got that 4r squared equals to 144.444. We'll divide this equality by 4. We will get that r squared equals to 36.111 units. Okay, so r squared equals to 36.111. We know that the area of any circle in the world equals to pi times the radius squared. The area of any circle equals to pi times the radius squared. We know that the radius squared equals to 36.111, so the area of this circle will be pi times 36.111, okay? We can put here the value of r squared and substitute r squared by 36.111, and we will get that the area of the circle equals to pi times 36.111 square units. Okay, so we got that the area of the circle equals to pi times r squared. The r squared equals to 36.111, so the area equals to pi times r squared. Pi times r squared is 36.111. Or in terms of number, it actually equals to 113.45 0.45 square units. So in terms of numbers, the area of this circle equals to 113.45 square units, or you can say that the area also equals to 36.111 times pi units, or the best way to say is that the area equals to 113.45 square units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the area of this circle, and inside the circle we have a shape, and we know the two angles of this shape are right angles, and side AD of the shape is 4 units, side DC is 6 units, and side BC is 8 units, and we want to find out the radius of this circle. Okay, in the first step I actually explained you the theorem of one-sided angles. Okay, actually, if we have two lines, line A and line B, and a third line C that intersects those two lines at points M and at point N, then alpha and beta defined as interior one-sided angles, and if alpha plus beta equals to 180 degrees, then line A is parallel to line B, and we can also have an exterior one-sided angles. The reason that they are called one-sided because of the fact that both of them are from one side of this line C. Okay, and those angles alpha and beta are defined as exterior one-sided angles, and there is the same rule that apply to them. This is to say, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay, the same rule of the one-sided interior angles. If the sum of either of the exterior angles is 180 degrees of the sum of the interior angles are equal to 180 degrees, then line A is parallel to line B. Okay, so actually rule number 1 states that if the sum of two one-sided angles, it doesn't matter if it is interior or exterior angles, so if the sum of those two one-sided angles equals to 180 degrees, then we can deduce that line A is parallel to line B. Okay, if the sum of those two one-sided angles equals to 180 degrees, then line A is parallel to line B. The same rule here is the same. If alpha plus beta equals to 180 degrees, then line A is parallel to line B. So actually we have in our circle we have angle ADC that equals to 90 degrees, and also angle BCD equals to 90 degrees, and both of them are one-sided angles. We can relate to AD as line A, BC as line B, and DC is line C that intersects those two line segments at point D and point C. So those two angles are one-sided interior angles, and the sum of those two angles equals to 180 degrees, because it is 80 degrees plus 80 degrees. The sum of them is 180 degrees. We have two one-sided angles, that the sum of those two one-sided angles equals to 180 degrees. For that reason, AD is parallel to BC. According to rule number 1, AD is parallel to BC because those two one-sided angles, the sum of them is 180 degrees. So according to rule number 1, AD is parallel to BC. Okay. Then we actually connected points D and B by a straight line, and also we connected points A and C by a straight line, and we actually created here two triangles, two green triangles, and we proved that three angles in this big green triangle are equal to three angles in this small green triangle, because angle AOD equals to angle BOC, because they are vertex angles. Actually, vertex angles are defined if you have two lines that are intersecting each other at the point of intersection, that is to say at this point, they create four angles. 1, 2, 3, 4. And actually angle 1 and 3 are defined as vertex angles, and according to rule number 2 they are equal to each other, and also angles 2 and 4 are vertex angles, and according to rule number 2 they are equal to each other. So actually rule number 2 states that vertex angles are equal to each other. Okay, so those two angles, alpha and beta, are vertex angles, and according to rule number 2, they are equal to each other. And the other possibility of vertex angles is those two angles are also vertex angles, and according to rule number 2, they are equal to each other. So actually we can implement this rule. We implemented this rule in those two green triangles. Angle AOD and angle BOC are two vertex angles, and therefore according to rule number 2 they are equal to each other. And then we actually have angle OAD that equals to angle BCO, because they are alternating angles. If we have two lines A and B and that are parallel to each other, and we have the third line that intersects those two lines at these points, then here angle alpha and beta are alternating angles, and alternating angles between parallel lines are equal to each other. Okay? If we know that line A is parallel to line B, then angles alpha and beta are alternating angles, and they are equal to each other according to rule number 3. Okay, those are interior alternating interior alternating angles, and if line A is parallel to line B, then they are equal to each other. Alpha equals to beta, and those are exterior alternating angles. In the case that A is parallel to B, then we have here two angles, alpha and beta, that are defined as exterior alternating angles, and according to rule number 3, they are equal to each other. So rule number 3 states that alternating angles between parallel lines are equal to each other. Okay, so according to rule number 3, we have angle OAD and angle BCO. Those two angles are alternating angles because we have AD that is parallel to BC, and those two angles are alternating angles between parallel lines, and therefore they are equal to each other. And in the same way, we can say that we have those two alternating angles between parallel lines. AD is parallel to BC, so those two alternating angles are equal to each other according to rule number 3. So we actually proved that 3 angles in this big green triangle are equal to 3 angles in this small green triangle, because this angle is equal to this angle. They are vertex angles. This angle equals to this angles. They are alternating angles, and also this angle equals to this angle. They are alternating angles, and according to rule number 3, they are equal to each other. So we actually proved that 3 angles in this green triangle are equal to 3 angles in this green triangle. For that, so we actually proved that those two green triangles are similar triangles. Okay, and therefore we have a special relationship between similar triangles. If we know that the big triangle ABC is similar to the small triangle DAF, then AB over DF equals to BC over EF, equals to AC over DF. Okay, so we proved that those two green triangles are similar triangles. Therefore, we can say that OB over OD equals to OC over AO. That equals to BC over AD. Okay? According to the rule of similar triangles, we have this relationship between those two green triangles, and we know that AD is 4 units and BC is 8 units, so BC over AD is 8 over 4, it equals to 2, and we got the equality that OB equals to 2 times OD from this equality, and OC equals to 2 times OA. So actually we know that if OD equals to A, then OB is 2 times A, and if AO equals to B, then OC equals to 2 times B, and then we know the next step. We know that triangle ADC, angle ADC equals to 90 degrees, so triangle ADC is a right triangle, so we can implement the Pythagorean theorem in this right triangle. We can say that the square of the hypotenuse, that is to say AC square, equals to AD square plus DC square. Okay, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So AC square equals to AD square plus DC square, and we know that AC equals to 3 times B. B plus 2B is 3 times B. We know that AD equals to 4 units and DC equals to 6 units. We put all the data here, and we got that the result that B equals to 2 over 3 times root 13, and 2 times B equals to 4 over 3 times root 13. And in the same way, we know that also angle BCD is a right angle. Therefore, triangle BCD is a right triangle. Therefore, we can implement the Pythagorean theorem in the right triangle BCD. We can say that the square of the hypotenuse, that is to say DB square, equals to the sum of the squares of the perpendiculars, equals to BC square plus DC square. Okay, BD square equals to DC square plus BC square. We know that DB equals to A plus 2A is 3A, and we have all other the value of DC and the value of BC, and we can put the data in this equation, and we found out that the value of A is 10 over 3, and the value of 2 times A is 20 over 3. So we actually have all the values of all the line segments inside this circle. Okay, so we can, I copied this drawing to this page, and in the next step we extended line segment AC until it touches the circle at point P, and we created new line segment CP, and we calculated the value of line segment CP according to the four full states that if two chords AB and CD are intersecting each other at point O, then the following equality is true: AO times OB equals to CO times OD. If chord AB intersects with chord CD at point O, then the following equality is true: AO times BO equals to CO times OD. So we can implement rule number 4 in our circle. because we have code AP that intersects, code AP intersects with code DB at point O. So we can implement rule number 4 here and can say that AO times OP equals to DO times OB. Okay, and we actually have all the data of all the line segments. We know the sizes of all the line segments inside the circle, so we can put the data inside this equality, and after we put the data inside the equality, we found out that the value of line segment CP equals to 16 over root 13 units. Okay, in the next step, we extended line segment DC until it touches the circle at point Q, and then we calculated the value of line segment CQ that was created. According to rule number 4, line segment chord DQ intersects with chord AP at point C. So, according to rule number 4, DC times CQ equals to AC times CP. Okay, DQ intersects with AP, so according, and the point of intersection is at point C, so DC times CQ equals to AC times CP. We have all the data, all the sizes of all the line segments here, so we put the data inside the equality, and we found out that CQ, line segment CQ equals to 16 over 3 or 5 1/3 units. Okay, and then we also extended line segment BC until it touches the circle at point R, and then we calculated the value of the new line segment RC. Actually, we have chord DQ that intersects with chord RB, and the point of intersection is point C, so according to rule number 4, DC times CQ equals to R to CB or BC times RC. Again, chord DQ intersects with chord RB at point C, so according to rule number 4, DC times CQ equals to BC times RC. Okay, DC times CQ equals to BC times RC. Again, we have all the values of all these line segments, so we put the data inside the equality here, and we found out that the value of RC is 4 units. Okay, RC equals to 4 units. So we actually found out the values of all the line segments inside this circle, and the only missing thing is the radius of this circle. And in order to find out the radius of this circle, we implemented rule number 5 here, and rule number 5 states that if two chords are intersecting at 90 degrees, then the following equality is true: 4R squared equals to AO squared plus BO squared plus CO squared plus DO squared. So actually, if we have two line chords, line chord AB and line chord CD, that are intersecting each other at point O is the point of of intersection, and they are intersecting each other at 90 degrees. That is to say, in the intersection point they create 90 degrees of each other. Then the following equality is true. 4 times r squared, r is the radius of this circle, equals to a all squared plus b all squared plus c all squared plus d all squared. Okay, so we can implement this rule in our circle, because we actually have here angle BCD equals to 90 degrees, and actually chord RB intersects with chord DQ at point C, and at point of the intersection point C we have 90 degrees, creates 90 degrees. So according to rule number 4, 4r squared equals to dc squared plus cq squared plus r plus bc squared plus rc squared. Okay, again, chord dq intersects with chord rb at point C, and at the point of intersection there is 90 degrees. Therefore we can implement rule number 5. Rule number 5 states that 4 times r squared equals to dc squared plus cq squared plus bc squared plus rc squared. And we know all the values of all the line segments here, so we put the data inside this equality, and we found out that the radius squared equals to 36.111 units. So the area of any circle equals to pi times the radius squared. So the area of this circle will be pi times 36.111 times pi square unit. So in terms of numbers, the area of this circle will be 113.45 square units. Okay, so the area of this circle equals to 113.45 square units. Okay, thank you very much.